Good morning. Today in this lecture onwards, we are going to discuss a new topic which is familiar to you, the thermodynamics. As you know, the study of any special branch of natural science starts with a separation of restricted region of space or a finite portion of matter from its surrounding by means of a closed surface called the boundary. So boundary is a closed surface that separates the system from its surrounding. The region within the arbitrary boundary and on which the attention is focused is called the system, and everything outside the system that has a direct bearing on the system's behavior is called the surrounding. The surrounding may be another system. So these are some of the terms which we usually come across in thermodynamics: the boundary, system and surrounding. So boundary is actually the closed surface that separates the system and surrounding. System is the region within the arbitrary boundary and on which our attention is focused, or the part of the universe under the investigation is called the system. The rest of the thing, or the rest of the universe, or the rest of the space excluded from the system or outside the boundary, which has a direct bearing on the behavior of the system, is called the surrounding. Depending upon the exchange of matter between the system and surrounding, we can define two types of system: the closed system and the open system. So if you consider some arbitrary boundary, then if we are investigating or studying the properties of the region of the space within this arbitrary boundary, then it is called the system. Then the outside world, which has a direct bearing on the behavior of the system, is called the surrounding. And this is the boundary. Now, if no matter crosses the boundary, that is, suppose the matters are within the system, the matter within the system is not crossing the boundary, then it is called a closed system. So there is no exchange of matter between the system and surrounding, or energy between the system and surrounding, which is called a closed system. Now an open system means there is an exchange of matter between the system and surrounding. So to discuss a system, we can have two point of view, or we can adopt two point of view to discuss a system, or to discuss the properties of a system, or to discuss the characteristics of a system. That is the microscopic approach and the macroscopic approach. The microscopic approach, which considers the variables or characteristics of a system at approximately the molecular scale or smaller. That is, we are considering the variables or the characteristics of the system, or the parameters which characterizes the behavior of the system in the microscopic level. Or microscopic level means in the molecular scale or smaller. If we consider the branch of physics like quantum mechanics or statistical mechanics, etc., where we are treating the system in the molecular level or smaller, or in the microscopic level. If you consider the other point of view, that is the macroscopic approach, where we are considers the variables or the characteristics of a system at approximately human scale or larger. Examples are the pressure, volume, temperature, mass, composition, etc. are the variables which are in the macroscopic scale. But if you consider the motion of an electron within an atom, or the energy of the individual atoms or electrons or the nucleons, atoms in a molecule or electrons in an atom or nucleons in a nucleus, etc. are the properties or the variables in the microscopic level. So in thermodynamics we will have this microscopic point of view. So the thermodynamics was used in all branches of physics and chemistry whenever we have to deal with heat and its relationship to energy of another form, like mechanical energy, electrical energy, magnetic energy, chemical energy, etc. That means if there is a reaction or process which takes a conversion or the interrelationship between the heat energy and other forms of energy, we will use thermodynamics. So in thermodynamics we are concerned with the study of the interior of a system, but describe it in terms of the macroscopic quantities which have a bearing on its internal state. That means if you consider the pressure, volume, temperature, etc., the entropy, etc., they are all macroscopic quantities or macroscopic variables. Using these macroscopic variables, we will try to describe the interior of the system or the behavior of the system. That is what we are doing in thermodynamics. So now if we focus on thermodynamics, we can have the thermodynamic variables or thermodynamic coordinates. Also we can have the thermodynamic system. So thermodynamic variable coordinates or the state variables of a system are the macroscopic quantities that has a bearing on its internal state and which is used to describe a system. So the pressure, volume, temperature, etc. are called the thermodynamic variables or thermodynamic coordinates, or simply the state variables. So which are the macroscopic quantities that has a bearing on its internal states or a bearing on the system's internal states, and it is used to describe the system. Now if you consider a system which is described by a thermodynamic coordinates or state variables, which is called a thermodynamic system. That means a thermodynamic system can be defined as the region of space or a part of universe within the arbitrary boundary on which our attention is focused, and the behavior of that system or behavior of that region is described by the macroscopic quantities like pressure, volume, temperature, or the thermodynamic coordinates or state variables. Now, if you consider a gaseous system, you know that to describe the behavior of a gaseous system completely, we use the state variables pressure, volume, temperature and entropy. So, pressure, volume, temperature and entropy are the thermodynamic coordinates or state variables of a gaseous system. Here gaseous system is a thermodynamic variable. Now, if you consider a liquid system, the corresponding thermodynamic variables which completely defines a liquid system are the volume, temperature and the surface tension. Now, if you consider a voltaic cell which is also a thermodynamic system, there we can have an exchange of or interrelationship of heat energy to other forms of energy. In the voltaic cell, the thermodynamic coordinates are the EMF of the cell, the charge on the battery or the cell and the temperature. So, in all these things you can see the temperature is one of the thermodynamic coordinate. Now, I told you that in order to describe a system, we need some variables or if it is a thermodynamic system, we need thermodynamic coordinates or the macroscopic quantities. The macroscopic quantities like pressure, volume, temperature for a system will have certain interrelationship, or we can form some equations connecting the thermodynamic coordinates of a system, which is called the equation of a state. So, in thermodynamics, the equation of a state means it is the equation representing the interrelationship between the different thermodynamic coordinates used to describe that system. So, this equation of state actually expresses the individual behavior of the system. You are familiar with the ideal gas equation PV is equal to nRT. Here it gives the interrelation between the pressure, volume and temperature of a thermodynamic system or an ideal gas, and this is the equation of state for an ideal gas. So, in thermodynamics, what we are going to do is we have to define the thermodynamic coordinates first, that is the macroscopic quantities that is used to describe the system completely. Then we should have a equation of state, that is there is a equation which connects the different thermodynamic variables describing that system. So, now let us start our discussion of thermodynamics. In the beginning, in order to simplify our discussion, we shall deal only with the systems of constant mass and composition, each requiring only one pair of independent coordinate for its description. So, what we are going to do is, for simplicity, we are considering a system which is having a constant mass and composition. So each system, if you are having a system like this, it requires only one pair of independent coordinates for its description. So let's say x and y are the two independent coordinates or thermodynamic variables or the state variables used to describe this system. Then if you consider any state of the system in which the coordinates x and y have definite values that remain constant as long as the external conditions are unchanged, is called an equilibrium state. So here in this lecture onwards, we are going to discuss the equilibrium thermodynamics. So what equilibrium state means, that if you are having a system and which is described by two independent thermodynamic variables x and y, and these independent variables have a definite values for a state of the system, and these variables remains constant as long as the external conditions are unchanged, then the system is said to be in equilibrium. So the equilibrium state of a system can be defined as the independent thermodynamic variables of a system has definite values and that remain constant as long as the external conditions are unchanged, then the system is said to be in equilibrium state. So what we are going to specify is that if you are having a system, let's call it as a system A, which is having a uniform mass and composition. For the sake of simplicity for our discussion, we are considering the systems which are having constant mass and composition, and also we consider that only one pair of independent coordinates are needed to describe the system. One pair of independent coordinates means if you consider two coordinates x and y, the value of x is independent of value of y, then these two coordinates, which is called a pair of coordinates, is needed to describe this system completely. In that case, if you consider the system is in a particular state which is characterized by the state variables x and y, or the independent variables as values x and y, then if you are not changing the external conditions of the system, then the state of the system remains the same with the definite values of these independent coordinates, then that system is said to be in equilibrium state. The experiments shows that the existence of an equilibrium state in one system depends on the proximity of other systems and on the nature of the boundary or the wall separating the different systems. But I told you that suppose the system is in equilibrium state with coordinates x and y, then the system is in equilibrium, then the existence of this equilibrium state depends on the proximity of other systems. That is, if you are having another system here, then the equilibrium state of the system A will depend on this system also. If it is B, if there is another system C here, then the equilibrium state of A will depend upon the presence of the systems B and C, and also on the nature of the wall separating the system and its surrounding, or system and different other systems. So actually the equilibrium state of A depends on the presence of or the proximity of other systems, and also the nature of the boundary of this system A. So this, on a broad classification, we can, based on the equilibrium state achieved by a system or the equilibrium state of a system, we can have two types of boundaries. They are called adiabatic wall and diathermic wall. So the boundaries can be either adiabatic or diathermic. If you consider a system A, this is a system A, and another system B. The system A has coordinates or thermodynamic variables x and y, and the system B has thermodynamic variables x prime and y prime. Then an equilibrium state for the system A may coexist with any state of the system or any equilibrium state of the system B for all attainable values of the four quantities x, y, x prime, y prime, provided that the wall is able to, this is the wall separating the two systems, that wall is able to withstand the stress associated with the difference between the two sets of coordinates. So if there is a difference between these two sets of coordinates xy and x prime y prime, then there will be a stress on this wall due to the difference in between these two coordinates, two pair of coordinates. Then if the wall separating the systems A and B are able to withstand the stresses on this wall due to the difference in the sets of coordinates or pair of coordinates, then the system A will coexist in equilibrium with the system B for all attainable values of x prime and y prime. That means if the system B is in any state having the values x prime and y prime, the system A will be in equilibrium. Then that wall is called a adiabatic wall. So an adiabatic, and if you consider an equilibrium state of system A may coexist with any equilibrium state of B for all attainable values of the coordinates of the system B. That means this wall serves as an adiabatic wall which can withstand the stresses associated with the difference between the two sets of thermodynamic coordinates. So the adiabatic wall prevents two systems from communicating each other. That means if the initially suppose the system A is in the state characterized by the coordinates x and y, and system B is in the state defined by the coordinates x prime y prime. Suppose the system B has been changed to some other values of x prime, y prime, which is again in another equilibrium state of B, then that won't change the system A. The system will still be in equilibrium state defined by the coordinates x and y if this wall is adiabatic. If this wall is not adiabatic, some communication will pass to the system A through this wall due to the change in the state of the system B. So, if the system A coexists with any equilibrium state of B, then if they are separated by a wall, then this wall will be an adiabatic wall. So, if a wall is adiabatic, then the system A does not know the changes in the state of B, which means that this wall, adiabatic wall, prevents the two systems communicating with each other. There is no way of communication between the two systems A and B if they are separated by an adiabatic wall. Now, if you consider the other type of boundary, which is called the diatomic wall, the values of xy and x prime, y prime of A and B will change spontaneously until an equilibrium state of the combined system is attained. That means, if suppose two systems A which is characterized by the coordinates x and y, another system B which is characterized as defined by the coordinates x prime, y prime, then if they are not in equilibrium and if it is separated by a diatomic wall, then these values of x, y and x prime, y prime will spontaneously change until an equilibrium state of the combined system is obtained. This is obtained by communicating these two systems A and B by exchanging heat from one system to the another. That means boundary through which heat is communicated from one system to another system yet remain close to the transport of matter is called a diatomic wall. So, this diatomic wall, if a system is surrounded by a diatomic wall, it is an example of a closed system because there is no exchange of matter, or matter cannot cross through the diatomic wall, but heat can be communicated from one system to another or across the diatomic wall. So, diatomic wall is a boundary through which heat is communicated from one system to another. But adiabatic wall is a boundary through which neither heat nor matter is communicated or exchanged from one system to another. Now, if you consider two systems, they are separated by a diatomic wall, then we know that the coordinates or the state variables of the two systems will spontaneously change until an equilibrium state of the combined system is attained. Then these two systems are said to be in thermal equilibrium. The example for a diatomic wall is thin metallic sheet. So, we are going to first of all focus on the systems which are separated by a diatomic wall. So suppose if you are having two systems A and B, they are separated by a diatomic wall, then the state variables or thermodynamic coordinates of these systems A and B will spontaneously change to acquire an equilibrium state of the combined system, and that equilibrium state is called thermal equilibrium. So thermal equilibrium is a state achieved by two or more systems characterized by restricted values of the thermodynamic coordinates of the systems after they have been in communication with each other through a diatomic wall. So using this concept of thermal equilibrium, in 1931 Ralph Fowler introduced one of the important law in thermodynamics, which is named as Zeroth law of thermodynamics. It is introduced by Ralph Fowler in 1931. It is named as zero because the first and second law were introduced much before the statement. So you know that thermal equilibrium is the state achieved by two or more systems characterized by restricted values of the coordinates of the systems after they have been in communication with each other through a diatomic wall. So when two systems are separated by a diatomic wall, then they will be in thermal equilibrium. Now the zeroth law of thermodynamics says that if two systems are in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. To get an more idea about it, consider this diagram. Here you can see three systems: system A, system B and system C. Here this line actually represents suppose a diatomic wall, and this wall suppose it represents an adiabatic wall. So no heat or matter can be exchanged between A and B. Now if they are separated by you can see that A and C are separated by a diatomic wall. So the systems A and C are in thermal equilibrium. Similarly, B and C are separated by a diatomic wall again. Then B and C are in thermal equilibrium. Now if you consider this one, here you can see that the system C is separated from A and B in thermal equilibrium. Then C is separated from A by a adiabatic wall, and C is separated from B by again an adiabatic wall, and A and B are separated by a diatomic wall. So A and B are in thermal equilibrium. So this is the condition you can see here, that is obtained from the zeroth law of thermodynamics. Here the zeroth law states that A and B are in thermal equilibrium with the third system C. That is, according to this diagram, we can draw this one. A and B are in thermal equilibrium with the third system C. Then A and B are in thermal equilibrium with each other. So that is zeroth law of thermodynamics, which actually establishes the basis for the concept of temperature and for the use of thermometer. So zeroth law is actually establishes the concept of temperature. So the statement of zeroth law of thermodynamics is that if two systems are in thermal equilibrium with a third system, or if two systems are separately in thermal equilibrium with a third system, then these two systems are in thermal equilibrium with each other. That is what pictorially represented here. That is, the systems A and B are in thermal equilibrium with a third system C, then A and B will be in thermal equilibrium with each other. So that is the zeroth law of thermodynamics, which actually establishes the concept of temperature and for the use of thermometers. So that's all about the zeroth law of thermodynamics and thermal equilibrium. Thank you.